Today I'm explaining about artificial neural networks. It's a part of the machine learning. In artificial neural networks, main objectives are neural network representation, appropriate problems for neural network learning participants, and multi-layer networks and backpropagation algorithms. In part 2, artificial neural network remarks on the backpropagation algorithm and illustrated example, face recognition, advanced topics in artificial neural networks. These are the artificial neural network objectives. Evaluation has one more is there, that is motivation, estimation, hypothesis accuracy, basics of sampling theory, a general approach for deriving confidence intervals, defense in error of two hypotheses, comparing learning algorithms. Right? To see in artificial neural networks, mainly that is three types. First one is neurons and biological motivation, neural network representation, and the third one is problem solve neural network learning. See, in perceptron, again in perceptrons we have two types, representations of power of perceptrons, the perceptron training rules, and coming to third one, multi-layer networks and the backpropagation algorithm. In that, again we have two subpoints, a differentiable threshold unit, and second one is the backpropagation algorithm. See, artificial neural networks. Artificial neural networks, nothing but human functionalities are converted into artificial. It is called artificial neural network, right? So, neural network learning method provide a robust approach to approximating a real valued, discrete valued, and the valued target function. Next, artificial neural network learning is well matched for certain kinds of problems like interpret complex real-world sensor data, speech or recognition, visual scenes, learning, robot control strategies, etc. Suppose coming to first point, that is interpret complex real-world sensor data. Data can be stored by sensor, means it is captured images, data in images captured and stored into the data. So speech recognition. While we are speaking with words, may not be correctly catch by the machine, right? So that time the machine will recognize the speech. Visual scenes also same. Suppose visuals maybe cannot be captured exactly around, if suppose 80% captured, then we can identify that image is correct. So remaining 20% will be recorded by the our artificial intelligence. Coming to third one, last one is learning about robot control strategies. Right. So see here, the back propagation algorithm is one of the efficient ANN algorithm which is useful in many practical problems such as learning to recognize handwritten characters, learning to recognize faces, learning to recognize spoken ones. The back propagation algorithm uses gradients for descent to few network parameters to best fit a training set of input. So neurons, neurons and biological motivation. The study of artificial neural networks has been inspired by the observation that biological learning systems are built of very high complexity. non-linear parallel. The human body is made up of trillions of cells, right? So cells of the nervous system called nerve cells or neurons. Simple. Neurons is nothing but the human body is made up of trillions of cells. Cells of the nervous system is called nerve cells or we can call it neurons. These are specialized to carry messages through an electrochemical process. We will send message from one to the form of so neurons and biological and coming to this topic, neurons and biological motivation. Here, neurons have specialized cells as shown in this diagram. Right, these are the nucleus, metaposition, dendrite, cell body. Right, so like this, we can see axons. So neurons have specialized cells for what dendrites and axons. Dendrites bring electrical signals to the cell body and the axons take information away from the cell body. Right? And to a neuron identify, neuron dendrites are used to take input to neuron cell and axons are used to give output from that neuron cell, which may input to the another neuron, right? Yes. As shown in this diagram, these are the nucleus and cell body, right? You can see here on that a neuron, this is the neuron structure. These are the dendrites and these are the axons, right? You can see here clearly axons, synapse, dendrites. So communication between two neurons will be like this. This one pattern is one between the axons or as a medium. Neurons are uh, in, in the human brain, neurons are estimated to contain an interconnected network of approximately 10 to the power 11 neurons, each connected on average to 10 to the power 4. That's right. Neurons, neuron activity is typically excited through connections to other neurons, right? So signals can be transmitted unchanged or they can be altered by synapse. The synapse is able to increase or decrease the strength of the connection from the neuron to neuron, right? And cause excitation and inhibition, right? Okay, substance. This is where the information is stored, right? Artificial neural networks are close or loosely motivated by biological immune systems. There are many complexities to biological immune systems that are not modeled by aliens. So artificial, right? So the information processing abilities of biological neuron systems must follow from highly parallel process operating on representations that are distributed over many neurons. One motivation for ANN is to capture this kind of highly parallel computation based on distributed representation. See here, historically, two groups of researchers have worked with artificial neural networks. Artificial neural networks to study and model biological learning process to obtain highly effective machine learning algorithms, right? Coming to second point, that is neural network representation. Here, a prototypical example of ANN learning is ALVINN, Autonomous Land Vehicle in a Neural Network, is a perception system which uses a learning ANN is to steer an autonomous vehicle driving at normal speeds on public highways. See the input of this. We can observe here input. The input for the network is a 3 by 32 grid optical intensities obtained from a forward pointed camera mounted camera. We can observe here output also. The network output is the direction in which the vehicle is. The artificial neural network is trying to mimic the observed steering commands of a human driving the vehicle for approximately 5 minutes. ALVINN has used its learning network to successfully drive at speeds up to 70 miles per hour and for distances of 90 miles on public highways, right? So, one more thing we can observe here, what is that? Because in the next slides, it shows the network, it is using one version of the system and illustrate the kind of representation we can observe. Typically, any artificial intelligence, artificial neural network system, we can observe that in this diagram, in figure 1, you can see 30 output units. So 4 hidden units are there, 30 by 32 sensor input units. Right? So input may be like this. In figure 2 and figure 3, we can observe come to the ALVNN system uses back propagation to learn to steer an autonomous vehicle photo at top, right? So running with speed up to 70 miles per hour. The diagram on the uh, left side already we have observed now, figure 1. So how the image of a forward mounted camera is mapped to 960 neurons, which are feed forward to 4 hidden units connected to 30 output units. Already I observed that is the 30 by 32 weights into the hidden unit are displayed in the large matrix, right? With white blacks indicating positive and black indicating negative weights. As can be seen from these output waves, activation of this particular hidden unit encourages a turn toward the left. So see here, these are the inputs and this is a hidden layer, these are the outputs, right? So in each artificial neural network is composed of a collection of perceptrons grouped in a layer, right? A typical structure is shown, we can show shown below. Figure. You can note that the 3 layers. How many layers are there? 1, 2, 3 layers. For the so input layer, hidden layer, and then output layer, right? So 3 layers are there. Input, comma, intermediate layer is nothing but hidden layer, right? And output layer, which is after. Several hidden layers can be placed between the input and output layers. Problems for neural network learning. Neural network learning is well suited to problems in which the training data corresponds to noisy, complex sensor data, right? It's also applicable to problems for which more symbolic representations are used. The backpropagation algorithm used most commonly uses ANN learning techniques. Right? Here it is appropriate for problems with the characteristics we can observe here. Instances are represented by many attribute value pairs. The target function output may be declared value, real value, or a vector of several real, or we can call it a discrete value attributes. Right? The training examples may contain errors. So we have what we have to do is we have to clean the data before taking the data. Long training times are acceptable. Right? Fast evaluation of the large target function may be required here. One more thing is that is the ability of humans to understand the learned target function is not important. Learning a human is not important here. Learning machine is very important here, right? So all of you observe this illusion. Perceptrons. Coming to perceptrons, one type of artificial neural network system is based on a unit is called perceptron. Perceptron is nothing but a ANN system is based on a unit is called perceptron. You can see in below figure, this is called a perceptron. And ANN consists of perceptrons. Each of the perceptrons receives inputs, process, input, and delivers a single output, right? A perceptron takes a vector of real valued in, then calculates a linear combination of these inputs. After that, it returns one, returns one. If the result is greater than some threshold, and otherwise minus one as its output, right? So where each wi is a real valued constant, or where that determines the contribution of input xi to the perceptron output. So see here, representation of power of perceptron. We can view the perceptron as representing a hyperplane station of focus in the n-dimensional space of instructions that point. You can observe in this A and B. See here, the perceptron outputs of A is 1. For instances, right, on one side of the hyperplane, and outputs of A minus 1. For instances, lying on the other side, right? Okay. So see examples. We can be separated by a single perceptron or called linearly separated set of examples. You can see here, A and B are separated. A single perceptron can be used to represent maybe values of Boolean objects. For example, if we assume Boolean values of 1 is true, and minus 1 is false, then one way to use a 2-point perceptron to implement and function is to set the weight W is equal to minus, means negative values 0.8, and W1 is equal to W2 is equal to how much we can calculate here, 0.5 maybe, right? So this perceptron can be made to define the OR. OR means OR arbitrary function described by also threshold to W naught is equal to how much we will get here, minus 0.3, right? Minus 0.8 minus 5, 0.5, you can give it. After that, doing calculation, you will get values minus 0.3. Unfortunately, however, some Boolean functions cannot be printed by a single perceptron, such as the XOR function. Those are called what? Linearly non-separable training examples. These are we are talking about training examples. We are considering here training examples only. So representation power of perceptron. A single perceptron can be used to represent many Boolean functions and functions we can observe here linearly separated, right? OR function, R function, linearly separable, XR functions, non-linearly separable, right? The perceptron training rule. So we have to discuss about this now. It is very important. Let us begin by understanding how to learn these weights for a single perceptron. They are important to artificial neural networks because they provide the basis for learning network of many units, right? So several algorithms are known to solve these learning problems. How we consider two. First one is perceptron rule. Second one is delta rule. To see the perceptron rule, one way to learn an acceptable weight vector is to begin with random weights, then iteratively apply the perceptron to each training example, modifying the perceptron weights whenever it misclassifies an example. So this process is repeated until the perceptron classifies all training examples correctly. Weights are modified at each step according to the perceptron training rule, right? So which revises the weight Wi that is associated with the input xi according to the rule. So see the rule here, Wi implies, reverse implies Wi plus delta Wi, where delta Wi is equal to n of t minus 0 into xi, right? So in the above equation, P is the target output and O is the output generated by the person. And N is a positive constant for learning rate. If T is equal to minus 1, means negative value, and the O is equal to 1, then weights associated with the positive xi will be decreased rather than increased. First decrease and then increase. If T is equal to 1 and 0 is equal to minus 1, then weights associated with the positive xi will be first increase and then rather than decrease. So you can see this example also. If xi is equal to 0.4 and n is equal to 0.1, t is equal to 1 and 0 is equal to minus 1, then the weight update will be delta wi is equal to n of t minus 0 into xi. So how much we got here? 0.1. So the above learning procedure can be proven to converge within a finite number of applications of the perceptron training rule to a weight vector that correctly classifies all training examples, provided the training examples are linearly separable and provided a sufficiently small n is used. If the data are not linearly separable, convergence is not assured, right? Gradient. Next one is the perceptron training rule in the gradient descent and the delta rule we have here. The perceptron rule finds a successful weights vector when the training examples are linearly separable. It can fail to converge if the examples are not linearly separable, right? So, coming to second one, the second training rule called delta rule. Second one is delta rule. First one is perceptron rule, right? Don't forget that. And second one is training rule called the delta rule. It's designed to overcome this difficulty. The key idea of delta rule is to use gradient descent to search these space of possible weight vector to find the weight that best fit in the training method. Right? The rule important because gradient descent provides the basis for the back propagation algorithm. Okay, it can serve as the basis for learning algorithms must search through the hypothesis spaces containing many different types of continuously parameterized hypotheses. So the data training rule is best understand by considering paper training and training example, right? That is threshold structure. That is a linear unit for which the output is given by x0 O of x is equal to w. In order to derive a weight learning rule for the inner unit, let us begin by specifying a measures for the training of a hypothesis. That is weight vector, right? Relatively to the training example, although there are many ways to define this error, one common measure is this difference. Error of different hypotheses for a linear unit with two weights. What is the hypothesis actually? We are using this term here. So hypothesis is nothing but it is an assumption, right? The value may be like so gradient descent such determines a weight vector that minimizes E capital E by starting with an arbitrary initial weight vector, then repeatedly modifying it in small steps. For each step, the weight vector is altered in the direction that produces the steepest descent along the error curve. This process continues till the global minimum error is reached. Right? We can observe that here delta WI is equal to sigma D belongs to what? To capital D. D is in capital. Capital D is nothing but training outcome data set 3D minus 4D into xi. Then it will update the weights on Wi into Wi plus delta Wi. Here, the gradient descent algorithm for training linear units as follows. Pick an initial random weight. Apply the linear unit to all training examples, then compute delta W, right? So for each weight according to equation, update each weight Wi by adding delta Wi. Then repeat this process until you will get result. Derivation of gradient is simple. See, this is how can we calculate the direction of steepest descent along the error surface here. This can be done by computing the derivative of capital E with respect to each component of the vector W. W is nothing but the input here. This vector derivation is called the gradient of capital E with respect to the W written in W E of W. A linear unit for which the output is given by O of x is equal to W dot x of 1. This is how we can call it equation 1. In order to derive a weight learning rule for the linear units, let us begin by specifying these measures for the training error of a hypothesis. One common measure that will turn out to be specially converted, right? So that is a second equation second. E of W is equal to 1 by 2 into sigma D belongs to capital. Right? Just now we have discussed about this small d. It belongs to capital. D is nothing but training examples. Training examples in one data set, right? Data. small d having data in capital. So PD minus OD whole square, that is equation 2. This vector derivative is called the gradient of E with respect to the vector W naught to Wn, written delta E, right? So you can see here, same in equation 3, delta E W is equal, we can call this symbol dou E by dou W1, dou W1, dou E by dou Wn, right? Since the gradient specify the direction of steepest increase of E, the training rule for gradient descent is W to W, where W is equal to 4. This is equation 4, and coming to equation 5. Equation 4 can also be written as delta Wi is equal to minus n dou E by dou W, right? Wi, sorry. Which makes it clear that steepest descent is achieved by altering each component Wi of weight vector in proportion to dou E by dou W. The vector of dou E by dou W derivatives that form the gradient can be obtained by differentiating E from equation 2. You can see here equation 2, right? Dou E by dou W is equal to dou by dou W 1 by 2 into sigma small d belongs to that also belongs to capital D. CD minus OD whole square. I am bringing this 1 by 2 in front of writing as is. And then see here this square. I'm bringing here 2 of 2D minus here over here. And then dou E by dou WI is equal to the so we can say the equation 6. Substituting equation 6 into the equation 5L, we get weight update rule for gradient. Gradient descent algorithm. So we call gradient descent algorithm. Gradient descent training examples. N. Each training example is a pair of the form x, t, where x is the vector of input values and t is the target output value, right? X is the vector input value here, t is the target output value, and n is the learning rate. So initialize each wi to some small random value until the termination condition is met. Do repeat algorithm. See the algorithm here. Initialize each wi to 0 first. For each x comma t in training examples, do it. Input the instances x to the until and compute the output O. For each linear unit weight wi, comma, wi, see here, delta wi tends to delta wi plus n into t minus rho into xi, right? For each linear unit weight wi comma wi, do wi tends to wi plus delta w. Gradient descent. To summarize this gradient descent algorithm, training linear units is as follows. Series. Pick an initial random weight vector. Apply the linear until through all training examples, then compute delta wi for each weight. Update each weight wi by adding delta wi. Then repeat this process because the error surface contains only a single global minimum, right? So this algorithm will coverage to a weight vector with minimum error, regardless of whether the training examples are linearly separable. Statistic gradient. The key practical difficulties in applying gradient descent. Right. So see here, one common variation on gradient descent integrated to evaluate these difficulties is called incremental gradient descent, or we can call it alternatively stochastic gradient descent. Right. So we can see the modifying training rule is here. See, this is standard gradient descent, right? This is stochastic gradient descent. So weights are updated upon examining all the ingredients. In this, here in stochastic gradient descent, weights are updated upon examining each training example. So second, standard gradient descent requires more computation for weight update. But here in stochastic gradient descent requires less computation for weight understanding. So maybe some small remarks are there. Perceptron rule update weights based on the error in the threshold perception output, right? Averages after a finite number of iterations to a hypothesis that perfectly classifies the training data. Provide the training examples or linearly. Coming to this delta rule, so some two or three remarks are there. This is based on the errors in the unthreshold linear combination of are averages only asymptotically toward the minimum error hypothesis, possibly requiring unbounded time. So, but coverages regardless of whether the training data are linearly sorted. So coming to multi-layer networks are the kind of multi-layer network learned by the backpropagation algorithm are capable of expressing a rich variety of non-linear decision surfaces. It is possible for the multi-layer network to represent highly non-linear decision surfaces that are much more expensive than linear decision surfaces. For example, in figure 3.0, see here, the speech recognition task involves distributing among 10 possible vowels, all spoken in the context of H to B, that is, hid, had, head, hood, etc. Right? So, observing this, the network input consists of two parameters, F1 and F2, right? Often from a spectral analysis of this sound, the 10 network outputs correspond to the 10 possible words. Okay? So the plot on the right illustrates the high nonlinear decision set. You can observe here multi-level network. Here we have input layer, hidden layer, and output layers. Right? In hidden layers, again we have two types: first hidden layer and second hidden layer. Multi-layer network, differentiable threshold unit here. See, like the perceptron, the sigmoid unit first computes a linear combination of its inputs, then applies a threshold to the result. In the case of sigmoid unit, however, the threshold output is a continuous function of its input. The sigmoid function, sigma of x, is also called the logistic function. See here one more interesting property. Output ranges between 0 to 1, increasing monotonically if it's input. You can derive gradient descent to frame, right? So one sigmoid unit here, multi-layer networks of sigmoid units implies to back propagation. Two-layer back propagation networks. input signal, error signal, input layer and output. So the back propagation algorithm, we can learn the ways for a multi-layer network. Given a network with a fixed set of units and the interconnections, it implies a gradient descent to attempt to minimize this squared error between the network output values and the target values for these outputs. Considering networks with multiple output units rather than the single unit, we define capital E to sum the errors over all of the network output units. So where output unit is the set of output units in the network. So EKD and OKD are the target output values associated with the gate output unit training example. The learning problem in backpropagation is set to search a large hypothesis space, define all possible values for all the units in the network. Right? So in multi-layer network, the error surface can have multiple local minimum. Minimum. The gradient descent is graduated only to coverage towards some local minimum, but not necessarily to global minimum error. You can see here backpropagation algorithm training example. This is a training example here. Creating feed forward network. Initialize all network weights to small random numbers. Example between minus 0.05 to 0.05, right? Until the termination condition is met. So you can observe here then some steps for backpropagation. The algorithm here applies to layered feed forward network containing two layers of sigmoid units, with units at each layer connected to all units on the preceding layer. Some notations are there. An index of the integer is assigned to each node in the network, where a node is either an input to the network or the output from unit to the network. The algorithm starts by constructing a network with the desired input and realizing all networks. So